Hello students. So in this lecture we will be discussing about quantum dots and the application of these quantum dots. Now quantum dots, as we have already seen, it is basically a nano material or a quantum structure where the quantum confinement has taken place in all the three dimensions. So the degree of confinement is 3, and hence the degree of freedom is 0. Now, so here you can see that a 3D material, that is a bulk material, normal material, has 3 degrees of freedom. By degrees of freedom, we mean that the electrons can move in all the 3 directions. There is no restriction to movement of electrons. However, if we keep on making the sides nanometer in the nanometer scale, that means if we first say we make the x, we make the x1 x as a nanometric dimension, that it reduces to two-dimensional nanostructure, then that is a film. Then if we reduce another dimension, it becomes it becomes one-dimensional nanostructure, that is a wire. And lastly, if we confine all the 3 dimensions, then it becomes a zero-dimensional nanomaterial, and that is known as the quantum dot. Now, the properties of quantum dot or any nanomaterial where the quantum confinement has taken place, it depends upon the degrees of freedom, like the number of energy states available particular to any energy, and this is the degree of freedom. Now in the case of a quantum dot, the degree of freedom is equal to Dirac delta function, this one delta E, and if we plot it, it will just be horizontal lines, discretized in horizontal lines in space. Now what is the Dirac delta function? Dirac delta function is a function represented by the characteristics that at it is an it has got an intensity of infinite value at e is equal to 0. However, apart from that, the intensity, the Dirac delta function value is 0. So, although it is represented by a peak-like function, it has got a peak and it has got also a band. Like any signal, the band width is almost equal to 0. And another property is that even if the bandwidth is approaching 0, almost equal to 0, the area under the plot is always 1, that is, it is normalized function. Right. So these sort of delta functions are basically used in various areas of science and engineering, like in signal processing, in quantum mechanics, in electromagnetism, in probability theory, and in Fourier analysis. Now, Fourier analysis, if you do the integral transform, that is the Fourier and the Laplace, they will also give the value to be equal to 1. And in quantum mechanics, any potential well can be represented by this delta function. So if V is the potential value, if it gets multiplied by this delta function, it has the properties of a potential well, and also the probability density, where psi is the wave function and the probability density is psi square. It also gets the probability density has also a delta function component, delta is x dot with it. So these are the properties. So basically, this is what is making the density of states at discretized energy values to be having a certain amount of so this is the forbidden space. There is no value in the lines between. So this is how this database is represented. Now another aspect of quantum dot, especially if it is a semiconductor quantum dot, is its quantum yield. Now, if it is a semiconductor quantum dot, then it will be used in harnessing light or in using it in optoelectronic instruments. Now, for those kind of use, a very important parameter is your quantum yield. What is a quantum yield? Quantum yield is nothing but the ratio of number of photons emitted by the number of photons absorbed by a fluorophore. Now, I'm going to what is a fluorophore. A fluorophore is a device that emits, that absorbs light at a certain wavelength, but due to its molecular structure, due to its structure, it emits light in a different wavelength. So the wavelengths of absorption and emission are not the same. This is what is known as a fluorophore. Now there are three different kinds of fluorophore. We classify fluorophore into three different types. First one is your organic fluorophore. That's organic dyes, and that is rhodamine, 6G is one of the rhodamine types, and fluorescein, that is FITC, organic dyes. Then we have inorganic materials like the quantum dots that we have just discussed, and the lanthanides, EU3 plus and Tb plus 3. They are also fluorophores. And in biological system, we have certain biological materials like, for example, green fluorescent protein, which can be said to be a fluorophore material. And the quantum yield, again, as we have said, that is the ratio of number of photons emitted by number of photons absorbed. We go into little details. So this is how mathematically you can represent a quantum yield. So here phi into I by sigma into P. So sigma is the cross section, P is the excitation power, phi is the fluorescent yield, and I is the integrated fluorescence intensity. So this is how the mathematical expression in more detail of a quantum yield is. Now the quantum yield of the is considered to be high if the value is between 0.5 to 1, and it is a medium if it is 0.1 to 0.5, 0.1 to 0.5, and if it is less than 0.1, then it is considered to be low. Now the materials or the semiconducting materials which can be made quantum dots are the following. For example, CD cadmium telluride has got a quantum yield of 0.3 to 0.7, which is said to be in between, falling in between medium and high value. Then we have cadmium telluride 0.2 to 0.6, PBS, lead sulfide 0.5 to 0.9, which is quite high here, and indium phosphide. So these all direct band gap semiconductors. They, if made into the form of a quantum dot, they are supposed to provide quantum leak in this range. Now another thing is that why do we call quantum three-dimensional nanometer-less quantum dot is, say, if this is the bulk, if we start with the bulk, which we normally consider a cube, if you keep on reducing the dimension, so it comes back to a point. It's no longer, although technically it is still a cube, but since it is getting confined in all the three directions, there is no point in making it of any geometrical shape like a cube. So we name it as a quantum dot. Okay. Now again, right. So now the materials that are usually the direct band gap semiconductors, which are made into quantum dots, are the 3, 5, 2, 6, and 4, 6. Silicon and germanium, the normal semiconducting material, they are indirect band gap semiconductors. indirect band gap semiconductors. They do not emit light. They, however, start to emit light only at nanoscale. At nanoscale, however, chances of light emission. There are chances of light emission in these materials, but we are not right now. We are not focusing on that. Now, these direct bandgap materials, like said, they can be made from group 3 and group 5 material, like here. So, like here, like the one we have just discussed, cadmium telluride. Sorry, cadmium telluride is like PBS. Take PB and S. So it becomes 4,6. This is a 4,6 material, PBS. Then indium phosphide. This is a 3,4 material, indium phosphide. And we do have a 2,6 material, which is in fact cellulite and telluride. In 2 we have this cadmium, so that cadmiums from CDSE and CDTE. Okay. Now, looking into the properties of quantum dots. Quantum dots have the properties of high quantum yield that we have seen, we have discussed, high QI, and also if we you can actually tune the wavelength by changing the size. I suppose that in case of a quantum dot, if you increase the size or the radius of the quantum dot, the wavelength absorption or emission, it shifts towards longer wavelengths. This is known as the redshift. Or hyperchromic shift, whatever you may call it. So, and it has less pronounced quantum properties. So the quantum properties they actually fall when if you're increasing the size of the quantum dot. Secondly, they can be used. A very impactful use of quantum dots is in something a device called single electron transistors, SET. Now, the transistor, as we all know, especially the field effect transistors, they have the components, the source, the drain, and in between there is the gate. So the voltage at the gate, it actually controls the flow between the source of between the source and the drain. And voltage at the gate is controlled by the electric field, the emission. So that is why it's called a field effect transistor. Now this field effect transistor, the properties can be enhanced, and it can be made a single electron transistor where the gate region here, this region, is just a conductor from an island or a quantum dot. Now what will this fabrication do is this fabrication will make the electrons as use a different color as the electrons, they move from source to the drain and from further. Now since it is quantized and the energy levels are discrete, only when there is a matching of energy level from the input and what is there in the quantum dot, only when there is a matching, there is a resonance created, the electron may flow. If there is no matching of energy levels, the electrons suffer a blockade and there is a gap, and that blockade is known as the Coulomb blockade. The Coulomb blockade. The electrons usually tunnel through the barrier, and the tunneling of electrons takes place one at a time. It's not that all the electrons tunnel simultaneously. So if the one, I say it is consisting of one electron. One electron has already tunneled, and so the Coulomb blockade mathematically, if there is one electron already present in the Allen region, the Coulomb blockade will or the resistance let's say it's basically change in energy. Coulomb blockade will be represented by E squared by 2C is the electronic charge, and C is interestingly the capacitance which is formed in this region. Okay. So there is a gate capacitance value. So there is a source, there is a drain, there is a gate, and in between this we have something called a gate capacitance. This is the gate capacitance C. The tunnel current which actually flows is due to the flow of electrons from source to drain or source to this island region, the tunnel current. It is again represented as E by delta t, the time period, into the Fermi-Dirac distribution. Actually, since we are dealing with electron, we are calling it as Fermi-Dirac distribution. Now, what is a Fermi-Dirac distribution? There are three types of statistical distributions. One is the Fermi-Dirac. The other two are the Bose-Einstein and the Maxwell-Boltzmann. So this Fermi-Dirac distribution it describes the probability of an electron. So let's call it a Fermi-Dirac. distribution or function. It describes the probability of an electron in a particular energy state in a system. It's the probability of electron in a particular energy state, Fe. The energy state is E, the Fermi formation is Fe. The Fermi Dirac is again represented in the following way. Fe is equal to 1 by e to the power E minus Ef by kT plus 1. If it becomes minus, then it is a Bose-Einstein condensation. Now, Fermi-Dirac distribution is followed by materials like electrons, then nucleons, whereas Bose-Einstein properties is followed by photons. All the integral spins, the particles having integral spins, that is photons, phonons, magnons, etc. And the last type is Maxwell's Boltzmann distribution, Fe, where F is equal to simply E minus Ef by kT. This is Maxwell's Boltzmann distribution function. Now, Fermi-Dirac distribution function, if you look at the function at E is equal to Ef, the Fermi-Dirac function Fe is equal to 0.5. So it implies that at Ef, the Fermi level in a semiconductor E has 50% occupancy. Whereas in contrast, in a metal at Fermi level, however, we are assuming that the measurement has been taken at 0 Kelvin. So in contrast, in a metal, and the Fermi level is considered to be the highest occupied energy level at absolute 0. So in metals, Ef is the highest occupied energy level at 0 K, whereas in because of semiconductor, it is the occupancy is considered to be the 50%. 50% states are occupied here. So this tunneling current, it follows. It has a Fermi-Dirac distribution function associated with it, and corresponding to that transfer of electron or tunneling of electrons, we will have tunnel conductance, or we should say this as the single electron transistor conductance, and it is equal to G, simply Gi by dV. Now, when we are using scanning tunneling microscope. Scanning tunneling microscope is a microscope used which is based upon the tunneling of electrons, and it is mainly associated with the molecular beam epitaxy. It can be a standalone instrument also, but usually molecular beam epitaxy has this term associated with it. And the first observed structure under STM was the silicon structure, silicon 111 surface, which has gone under reconstruction. And so this scanning tunneling microscope has an accessory called STS, scanning tunneling spectroscopy. So what does this scanning tunneling spectroscopy does? It simply uh, takes the di by dv plot, that is the conductance plot with respect to temperature. So basically it is finding the ACT conductance. Okay. Now the materials used in scanning in a single electron transistor. So let's recapitulate a little bit of things that we were discussing about quantum dots. Quantum dots are where you have the confinement degree of confinement as 3 and degree of freedom as 0. So this quantum dot has got many uses. Firstly, in electronics, in optoelectronics and optoelectronics, the quantum dot of light or a direct bandgap semiconductor, a quantum dot made out of that, has got very high efficiency. Quantum yield is very high, and also the in terms of electronic motion, if you're not focusing on the light emission but the transistor or any device fabrication which requires current, so it can be used as a single electron transistor which follows the property of Coulomb blockade. Okay. Now, now this, this single electron transistor. Now looking closely again to the quantum dot applications. The quantum dot can be applied to now the reason why this quantum dot has these enhanced properties is due to its confinement. So by confinement we mean that it has the energy states separated enough. So the confinement, it indicates highly separated highly separated energy states. By separated energy states mean an energy state which will have confined states which are highly separated from each other. This one, like this one here, like in a semiconductor, in a semiconductor quantum dot, and the valence band and the conduction band, in both these cases in the energies are discretized. So a conduction will have a discrete energy level and the valence band will have another again discrete energy level. So the transfer of electron will take place in these levels, and so there is a tuning of electron possible. By tuning a wavelength which is getting emitted is possible, and these discretization of states, they take place based upon the size of the electron. So indirectly the size of the electron is responsible for tuning the resolution of wavelengths of different color. Now due to this highly separated state, there is a again superior transport and optical properties, and they are used in different devices. For example, they are also used in junction diode, PN junction diode, where the quantum dot is applied at the junction. And so the each quantum dot is becomes unstable and emits photon. Since in a p-n junction, so this is the p side, then this is the n side, and we have put a quantum dot here in between the p and the n side. So what will happen, as said, the p side, the holes will go from p to n side holes, and electron will travel from n to the again the quantum dot formed. So, so since both of these states are quantized, so it becomes a little bit so it becomes tunable, as we have said, as we have explained. Now the emission energy, now this also becomes a little unstable due to the continuous flow of electrons and holes from either two sides. The quantum dots also becomes a little unstable. And the emission wavelength, however, as I have told you, it is depending upon the size of the electron, like here. So apart from the size, it also depends upon the effective mass and the carrier concentration. So either it depends upon Me star and Mh star, these are the effective mass inside the material, and the concentration of the charge carriers, that is electrons and the holes. Now, the molecular beam epitaxy is widely used to deposit these quantum dots, because it can take the shape and the size can be controlled with more precisely in case of a molecular beam epitaxy. Another application of this quantum dot is if you have a solar cell, a PIN solar cell, where there is an extra intrinsic side, which is usually undoped. So if you put a quantum dot in the intrinsic side in an array form, that means you have this p side and you have this n side. In between, these quantum dots are placed, which are identical, and in an array. This is the arrangement. This will lead to an increase in the efficiency of a solar cell, and it gets an increase up to 63%. However, it has been calculated theoretically. Experimental observations of 63% solar cell is still yet to be observed. Is yet to be observed. Okay. Now this intrinsic this PIN diode is again is the one which is placed for a certain reason. That means this PIN diode, this PIN region, is also known as the drift region, and it handles high voltage. It is used to handle high voltage and high power. High voltage, high power. By high voltage, I mean that about voltage of about 10 kilovolts, and by high power, means power of about 100 watts. And also this PIN, putting an interesting layer, it also helps in faster switching. Faster switching, that means the switching can be in nanosecond or microsecond time. So these are the applications of different applications of quantum dot. Now the different types of quantum dots and the quantum dots are most effective in the case of metals, in the case of semiconductors. If you make a quantum dot of metal, it may not be that much feasible simply because of the fact that it will have a Bohr exciton radius which will be not compatible. The reason. Now, other applications of quantum dots or other properties of quantum dots, if you see so, are the following. A quantum dot has a symmetric and a narrow full width half maxima. If you look into the emission and absorption properties of a quantum dot is the one which has very narrow full width half maxima. That is bandwidth. In short, bandwidth. It's very short. It is 25. Usually, it is 25 to 40 nanometers. And so this bandwidth, it corresponds to the photoluminescence spectra, the PL spectra in ultraviolet to near infrared regions can be obtained, and it leads to emission of pure colors. However, in contrast, if we compare these with the organic dyes like fluorescein, fluorescein has a bandgap high 150 to 180, 50 to 100 nanometers. So, unlike organic dyes, the semiconductor conductance, it shows a broad absorption spectrum. So, and also the high quantum yield means the high brightness. If the quantum yield is more, it will automatically mean that the brightness is high. And also another aspects of having high quantum yield, that it will have high resistance. to something called photo bleaching and chemical degradation. Photo bleaching and chemical degradation. So all these properties of quantum dots, along with the stability as well as the surface to volume ratio, which is common for all nanomaterial, it makes quantum dots superior to organic dyes in detection and sensitivity, and they can be used as sensors. They have higher sensing property than organic dyes, and they can be even used in making some new generation sensors. One of them is also known as robo biosensors, like drug delivery systems where the device itself identifies the region where the drug has to be deposited.